y squared. If a difference in y values is bounded above by the difference in x values, the distance between them, then we can get away with setting delta equal to epsilon and then proceeding wrapping up a problem the way we did the last one and proving that that 0 actually is the limit. Delta, then the difference between this and 0, which is less than this, also less than delta, which equals epsilon. Therefore, the limit of this function as x and y go to 0, 0 actually is 0, which is also the function value that we defined. So f is continuous at 0, 0. We already said it's continuous everywhere else, so this function actually is continuous everywhere. If I rewrite it this way, then, yeah, so then, because y is making a positive contribution to it, yeah, but this represents an upper bound. And yeah, so because the difference between function values is less than or equal to the difference between the point you're at and the point you want to approach, that's what lets us set delta equal to epsilon, instead of having to have some other relationship. If you find, through manipulations like these, that the difference between the function and the candidate limit is less than or equal to some function of x squared plus y squared, where the inverse function exists, and g is an increasing function. So in this example, g of z is equal to z, so that is an increasing function. Then you can set delta equal to the inverse function of epsilon. So in the last example, g of z was actually equal to 4z, so our inverse function was z over 4. So delta, we set delta to be epsilon over 4. So that's how you can choose delta in terms of epsilon to prove that the limit exists. So the hard part is this part, where you try to relate the difference between function values to the distance between x, y, and the point you're approaching. So if you establish a connection between those, then that's the key ingredient in establishing a limit. Differentiation. But since we're dealing with several variables, what we're really looking at is partial differentiation. So if you recall from single variable calculus, given a function f of x, the derivative of f at some point x naught, that's written different ways, if you remember, either f prime of x naught or df dx and x naught, and it's defined to be a limit where you take x naught and you perturb it by some value h, take the difference between that and the value at x naught, then divided by h, and you take the limit of that as h goes to 0. But when you have a function of several variables, then that means that there's different directions in which we can travel from the point x naught where we want to know the rate of change. We can go along the x direction, the y direction, the z direction, however many variables we have. So how does this generalize in the case of a function of several variables? Let's just look at two variables. So given a function f of x, y, the partial derivative of f, and here it's more important than ever to specify which variable you're differentiating with respect to. In single variable calculus, it's usually pretty obvious from the context, but not anymore. With respect to x, now again, there's different ways of writing it. So there's no more prime here, because prime doesn't indicate what you're differentiating with respect to. Don't use it. So often it's written this way. So it's a slightly different symbol. Instead of df dx, that's this symbol that kind of looks like a 2, but not like my 2's. Partial derivative with respect to x, evaluated at x naught, y naught. As I mentioned, we're looking at partial derivative at a particular point, any point. Another way of writing it, which I'll probably use more often because it's shorter, is you take a function and then you put the variable you're differentiating with respect to as a subscript, like this. So f sub x, and then the point where you want it. And this also is defined as a limit that closely resembles the one from the single variable case. But now what you do, you only add the h to the x variable because we're differentiating with respect to x. We leave a function fixed at a particular y value. F of x naught, y naught, all over h. So we're only seeing how a function changes along the x direction. So that only gives us part of the picture as to how a function behaves at that point in total. And that's why, to complete the picture, you look at the partial derivative with respect to y at that same point. So that would be partial derivative with respect to y, and then we have f with a subscript of y. And now we're going to have a limit. So now the x stays fixed, and we perturb the y value. That's f x naught, y naught, all over h. A good way to think of it is, if you want to differentiate with respect to x, you freeze the y value. You keep it fixed at that y value where you want a derivative. And then you think of this as a function of just one variable now, x. Same for differentiating with respect to y. You keep x fixed. Now you're looking at a function of one variable, and you see how it changes with respect to y. That allows you to apply all the differentiation rules that you're familiar with. Look at a simple example of fxy is equal to x squared times y. And we want partial derivatives at this point. X naught, y naught is equal to 2 minus 1. So here's what we can do. For partial derivative with respect to x at 2 minus 1, we can look at this function with y frozen at minus 1. So we can actually take the derivative with respect to x of f of x minus 1, so we'll just go ahead and plug in that y value right off the bat. So now we're back in single variable calculus. So when we plug in y equal to minus 1, we now have minus x squared. And I should mention another notation, this is in the notes, but I'll use it here. We also care about when x is equal to 2. So when we're done with this, we'll plug in x equal to 2, but we have to wait till the end. This is a common notation where you put a vertical bar, and you say x equal to 2. That means whatever this is, once we evaluate it completely, we plug in x equal to 2 at the end. Same thing here. It's kind of like with integrals. So for instance, if you had an integral like this, do the anti-differentiation, you get x to the 4th over 4, and you put the vertical bar, and there's 0 and a 3 to indicate you're going to evaluate this at 0 and 3. It's a similar kind of notation. So that vertical bar signifies we're going to evaluate this at something. So we just differentiate minus x squared in the usual way. So that's minus 2x, evaluate x equal 2, so we get minus 4. So we can plug in any variables we're not differentiating with respect to immediately, then we have a function of just one variable. The one we care about, we differentiate in single variable fashion, and then you're done. Let's do this for y. So now we're going to take f, we're going to plug in x equal 2 right off the bat, leave y unchanged, and differentiate that with respect to y. So when we plug in x equal 2, we get 4y. The derivative of that is just 4. This is a constant function. So at this particular point, I'm just going to do a general graph here. So here's the point when x is 2, y is minus 1. And we're looking at the function value there is going to be minus 4. So I'll go ahead and draw my free space. We'll try to get a feel for what these derivatives mean. So we know what it means in the single variable case. The derivative is a slope of a tangent line, instantaneous rate of change of a function. Now in this case, when x is 2 and y is minus 1, our function value is down here. So this is x is 2, minus 1, and the z value is going to be minus 4. We're computing partial derivatives at this point. Now, if the rate of change with respect to x is found out to be minus 4, what that means is, from this point, as x changes in this direction, the function is going to be decreasing at a pretty steep rate. So, however much x changes, the z value is going to be decreasing at a rate of that times 4, because partial derivatives with respect to x is minus 4. On the other hand, the partial derivative with respect to y is plus 4. So as y increases, goes this way, the function value is actually going up pretty sharply in that direction. So you could have a very different situation going on depending on which direction you're going in. You could have, so the graph of this function, it could be, if it were a curved surface, it could be something that's like saddle shaped, for instance, something like this. So x direction down here, going down here, y direction, the value is going up. That's just one possibility. So you have to know the whole picture. How is a function value changing in any direction? And later on, we're going to use this information to figure out in which direction is a function changing the fastest, in which direction is a function not changing at all. Because if a function is decreasing in the x direction, increasing in the y direction, there must be some direction in between where it's not changing, and that's actually where the level curves lie. If you know which direction the function is decreasing the fastest, then you might want to travel along that direction to find out where a function is at a minimum. So this is what the partial derivatives could be. They could be instantaneous rate of change or slope of a tangent line, but only going in that one direction that you're differentiating with respect to. But the most practical way to carry out differentiation is suggested by what we saw here, that you're differentiating with respect to one variable and you're freezing the other ones. So in general, the best way to go about this, you certainly don't apply the definition, you perform single variable differentiation with respect to a variable of interest. All other variables are treated as a constant. Now, it sounds like a simple idea, but in practice, it's the sort of thing where it's pretty easy, unfortunately, to make a careless mistake. So, for example, let's take a look at this function. E to the minus x squared plus y squared, sine 3x cosine 4y. And ultimately, you want the derivatives at this point, pi over 2 and pi. But the idea is, if you're asked for partial derivatives at a particular point, the best thing to do, wait until the very end. Don't plug in anything until you've completely finished differentiating. So what you would do is, let's take a look at partial derivatives with respect to x. So you have to apply the product rule, because this depends on x times this function, and also depends on x. But this function only depends on y. Treat y as a constant. All right, if you're differentiating with respect to x, treat y, whatever the other variable is, you treat it as a constant. But it's that important to remember. You can think of as a constant the whole thing, cosine 4y, and pull it out. So it's cosine 4y, and then you differentiate the rest of this with respect to x. So that's kind of nice, because then that's one part of a function that you don't have to think about anymore. Whereas if all of this was a function of x, in a single variable case, you'd have a lot more work to do. So now we'll focus on the rest of this using the product rule. So we'll have sine 3x times the derivative of this with respect to x. It's an exponential function, so you repeat the exponential function.